Well, that's a height, but how much does it actually weigh? It weighs like 14.7 pounds per square inch, that kind of thing. And so 14.7 pounds per square inch, that's like having 760 millimeters of mercury, or that would be like having what? 30 feet of water. But the thing is, okay, if you're under 30 feet of water, you'd be under 1 atmosphere pressure, correct? But let's say you're under 30 feet of water in a swimming pool versus under 30 feet of water in the ocean. Are you going to have the entire weight of the ocean on top of you, or just 30 feet? Just 30 feet. You know? And so whether you're in a deep swimming pool or the ocean, 30 feet is 30 feet, and therefore we can use height to measure pressure. And so a liquid height, that's because if you want the physics of it is that the pressure of a liquid is equal to rho GH. Rho is the density, or actually I should use D. You know, different books will use different symbols. I should say DGH. G, do you know what G is? G is gravity. Gravity is a constant at a certain height, 9.8 meters per second square. And what is H? Height. Now, does density change much for water? Yeah, it changes a tiny bit, you know, you go to the bottom of the ocean versus the top, but from 0 to 30 feet, does water density change much?
Not really.
Not really. Does the force of gravity change much? No. And so these two are constant. If these two are constant, then what we say is that the pressure of the liquid is directly proportional to its height. So that's where the relationship comes in, but I didn't talk about that. Okay. Does that answer it?
Yes.
39. C? Assuming barometric pressure 14.7 psi minus 5 psi G equals. Okay. Is that what everybody got? Yeah. 40?
Wait, how do you do 39?
39? 39, you just visualize a pressure gauge. Actually, can somebody answer that really quick while I get my thing? I'm just going to get something out of it. I'm just going to borrow somebody's soda can. They're in the back. I have some soda cans, but I forgot to bring them. But this I'm just borrowing the can because this is empty, right? And so if this is empty, what is the pressure inside the can?
14.7
PSI what?
8.
8. Or is there really any air pressure inside the can? Would you say? But what we could say is that there's zero pressure in the can because there's zero pressure in the can because there's no gas leaking out or no gas being sucked in. And so that we call, if I bought a pressure gauge, you know, like I bought some barbecue tanks. Barbecue tanks have a little pressure gauge for the propane. If I bought those and that propane gauge went to 0, then that tank is empty, but is it really empty? If I put that barbecue pressure gauge on this can, is it going to register pressure? It's going to be empty. There's no air pressure in here. And so the difference is, if I measure the air pressure inside this can with a barbecue pressure gauge, it's going to read 0. But there is air inside this, right? And so, and how much air is inside that? 14.7. So can you imagine they made barbecue gauges that read absolute pressure? People would be confused. People would be returning the tank complaining, hey, I still have 14.7 pounds of propane in here. I'm being ripped off because there's no propane coming into my barbecue, right? And so they better not write absolute, because people are going to think they're cheated, because, hey, I want every last drop of propane out of here. Are they going to be able to get every last drop of propane out of here? No. And so you might as well have it read 0, otherwise people are going to think they're missing propane. And the same thing here, we better put 0, because if you send this, hey, I have some canned air I'm going to send to China. Have you heard that it's very popular right now, canned air in China?
No.
It's very popular because of the pollution. And so they're sending, like, I saw there are a lot of businesses that sprung up. And not just China, but other places as well with heavy pollution, Indonesia and some others, I think. But, so I'm going to just put a piece of tape over here and then send this over there and say, here's my canned air. Help yourself. Good, clean, fresh California air. What are they going to do? They're going to go over here, peel off the tape and go, what? Now I got to suck out the air? Do you have enough lung power to suck out the air out of this? No. But you're going to say, hey, it's got 14.7 pounds of California air in there. Aren't you happy? No, you'd be very disappointed, wouldn't you? And so to show that, so we have 2 gauges. One gauge measures the absolute. Oops, didn't work. One gauge measures the absolute. The other gauge measures gauge pressure. And if you're going to sell canned air, the person buying canned air probably wants high pressure of air here so they can open a valve and let out some air to breathe that in, right? And so what I'm going to do is I'm just going to do a little demo of atmospheric pressure. And so I'm going to leave this mostly air. I'm going to just put a little bit of water in here. And so you can say, I have proof. I have proof I'm not ripping you off. I have proof that there's air in there. And so this is the proof that there's air in there. They might say, you sold me an empty can of air, but you say, hey, it's not empty. I'll prove it's not empty. What I'm going to do is I'm going to heat it up. Actually, I probably should have used it. Have you seen this?
Yeah.
Oh, I did it yesterday?
Oh, you want to see it?
I don't want to waste the time doing it again. I did this yesterday. Then I was confused. Were you here yesterday? Then it didn't make sense, the PSI-A versus the PSI-G? No? All right, then. You could say, I sold you air. It was just 14.7 PSI-A. You might have wanted 14.7 PSI-G. If you wanted 14.7 PSI-G, then there would have been 2 atmospheres of air, and it would have been high pressure air in there, right?
Just to go to clarify, 0 PSI-G is equivalent to 14.7.
Well, no, the way the gauges work is whatever atmospheric pressure is. 0 means no gas is going to leak out and no gas is going to leak in. So it depends on what atmospheric pressure is. So the gauges they have like 2 sides. One side,
the atmospheric or barometric pressure is pushing. The other side, the gas inside here is pushing. If it's reading 0, then the atmosphere and the gas are the same pressure. It's the same thing. And so anyway, let's just get this up. What a lot of people do in chemistry is these burners are meant to, so you could focus the heat in some places or others. So what I want to do is I want to put just the tip of the cone right there so it starts boiling faster. Do you hear it?
Yeah.
Okay, so I got the water boiling. And then you just generate steam. Why steam? Steam works a lot better because steam liquefies. So going from a solid to liquid, it collapses the volume much more. Okay, so this is boiling. And then, let's do this. Let's see how it works this time. Ready? Okay, so this can indeed has gas in it. We can see because this is going to kind of empty the gas out of there. This works better if this is ice water. So if I had some ice water, that cools it down even more. But I'll just use regular tap water here. Let's see. So there. So you just need powerful lungs to suck out the air. If you have powerful lungs, then no complaints. Everybody should be happy. Yeah, so that's 2 cans I wasted. These are somebody else's cans. I have to return those cans.
Okay, do you see some gas forming here? The problem is this power supply is too weak. We have a much better power supply, but it's way over there. So PSIG is the gauge. PSIA is the absolute. The thing you do is you just draw. If you want to do this, you just draw it. A gauge that shows both. If you draw a gauge that shows both readings, then 0 PSIA is equivalent to minus 14.7 PSIG, assuming that. And then 0 PSIG is equivalent to 14.7 PSIA. And then let's go with 2 atmospheres. So if we do 29.4 PSIA is equivalent to 14.7 PSIG. So you just draw something that shows both readings. This is like Celsius and Fahrenheit. They just have 2 different 0 points. That's it. And so how do you convert from Celsius to Kelvin? You add. How do you convert from PSIA to PSIG? You add 14.7. It's the exact same thing because the zeros are offset just like the Celsius and Kelvin scale, so we got to add. It's the exact same thing in Celsius and Fahrenheit, except we add 32, right? Because the zeros are offset. If the zeros match, then it's a different story. We could use dimensional analysis rather than algebra addition. 40. 41. False?
Yeah, it's only the vault and France, not uncertain.
Yeah, all measurements contain uncertainty is true. How can you read something so accurately and so precisely that there's no uncertainty? Like reading the lines. Can you read the lines exactly? You know, with the ruler? No. And that goes for everything. Even if you have a fancy instrument, there's still, and even if you have a fancy calculator, is there uncertainty in here? Yeah, because the calculator rounds off. That creates uncertainty. It's not exact. Does the calculator carry infinite digits? No. So the calculator is not. Unless you use fractions. If you use fractions, you can get around. Did I say about the Casio already? You can get around that. 42. 42 is
False.
false. 42 is false because of this.
I think the 41 is too big. Because if you're measuring quantity, you can be very certain about quantity.
I'm sorry?
I think 41 is too big. Because if you're measuring quantity or something, you can be very certain about your measuring
Oh, like
quantity.
people?
Yeah.
Alright.
Or like 1+1. Yeah, like if you were
But no,
counting
but
people in a room, so
okay.
you add more people, you're like, oh, well, you're not gonna have 0.8 people per person.
Okay. Well, 1+1 is like, where did the 1 come from? And you're right, it is vague. But if it's not stated, how many sig figs is that? If it's not stated. Automatically, do you say infinite, or automatically do you say 1? Automatically you say infinite? This is a measurement. If it's a measurement and you have 1, is that infinite? And so automatically there's uncertainty there because we don't know how it was measured. We don't know who did the count. So for example, you could be absolutely certain you counted the number of people in this room exactly, and then you verify it. But if you ask somebody to count the number of people in this room, you never know because everybody has a different standard. So for some people, they say, okay, I see about 30 people, so I'm just going to say 30, you know, and then leave it at that. And then you go, okay, they counted the number of people in the room, and so they must have counted it exactly. And so that breeds, there's uncertainty there. Obviously, we could define it as being exact, and that's what we did for a number of quantities. We defined it as being exact. Mm-hmm.
What if my doctor says, okay, take 2 pills per day? You wouldn't take that to mean, okay, I'm gonna take anywhere from 1.5 to 2.4 pills per day. You have to be very exact. Maybe
No,
take
no,
2.
no. I'm saying this is what I'm saying. I'm saying that yes, we can define certain things as being exact. We've done it a bunch of times. 18,000 gallons. 18,000 gallons. How many sig figs did I say? 2 or infinite? In this particular problem, I said we'll take this as infinite. So yes, we can define it, but that's me doing an extra step to define it. If somebody just said an 18,000 gallon pool, you can't automatically assume that it's exact. And as far as drug dosage goes, yes, you want to take those 2 pills exactly, right? But the actual drug dose is going to be depending on, you know, weight and other factors, you know. And so with that there is, but you know, it's true. There's always ambiguity. And so this is what I was saying about it earlier, but when we take an actual measurement, you know, well, I see what you're saying. And so, yeah, you could argue it.
So what you're trying to say is just that question is intended for just within the realm of chemistry, because you have to be precise, as exact as possible.
What I'm saying is this, because like when we did the 60 drops, how many sig figs did I tell you to put there? When you did the 60 drops of water, how many sig figs did I tell you to use? 1, 2, or infinite? I told you to use infinite sig figs. Why? Because I'm assuming you can count those exactly without missing one or accidentally dropping an extra drop in there or actually missing a drop. I'm just assuming you can count those exactly. But in general, if somebody were to come up to you and say, oh, I counted 60 drops, would you trust them? You know, do that? In general, if you take 2 tablets, you know, and I said I've taken 2 tablets, but if they have some memory issue or there's something else, you know, there's a human element to measurement. And so there's always that uncertainty, you see? And so even though, yes, I can count those exactly, and I'm going to define it as exact, you know, and we did it because we're confident that we can count. I can count the number of people in this room exactly, I just double check it. But in general, you know, there's going to be that uncertainty because if I count that, it's the same thing that happens.
you know, I was looking at measuring something, so I asked somebody to take some measurements, you know, but how precise they took the measurements is completely different than the measurements of another person. And so in that case, there is that uncertainty. You know, I trust you, you could do it exactly, but if I gave that to somebody else, Alzheimer's patient or somebody with memory issues, you know, did they take those 2? Did they take 3? You know, there's always that uncertainty. That's what I mean by uncertainty in measurement. You know, obviously, we can do exact things for integers. You know. How many cars? You know, we can do that exactly. But this is well known in science. We have to consider that all measurements contain uncertainty and then treat it. Now, how much is that uncertainty? That uncertainty can go down to 0, right? For big objects. It turns out from quantum mechanics, that uncertainty can never be eliminated. When we get to the very, very small level, you would think, okay, I can count anything exactly. No, you can't. At the quantum mechanical level, you can't. This is called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle is this: uncertainty. All measurements contain uncertainty. That's the Heisenberg uncertainty principle. At the very fundamental level. At a very we don't notice these things because we live in a macroscopic world. If we're living at the particulate world, then we notice these things big. All right, well, anyway, this, again, is debatable. I mean, if you came up to me and argued that 2 tablets, that's measuring it exactly, I'll take it. You know, I'll give it to you. You know, you just have to have an argument for it. Because can you make a rule for everything? Can you make a law for everything? No, you can't. And so we got to take it case by case. It's okay. But this is table salt. You have to know. You know, I talked about table salt. Table salt does not form molecules. What does table salt form? Crystal, and I called it a ionic lattice. And I said, don't worry about what ionic means. We'll talk about it later, but it forms a lattice. It does not form molecules. And the lattice looks something like this. We'll talk more about it later. But it forms nice crystals like that. But when you look at the arrangement of the atoms, the arrangement looks like this. When you look at the arrangement of atoms, you can't tell. You can't differentiate individual molecules in here.
That's why we can melt salt.
You can melt salt. You can melt salt. Yeah. But what things like ice melt at a very low temperature. You know, those molecular solids we say melt at a very low temperature. Wax is molecules. Ice is molecules. Lattices melt at a very high temperature. Salt, and what was the other lattice I gave you? Quartz was the other lattice I gave you. Quartz has a very high melting point, over 1,000.
What is the lattice?
LATTX. This is just, you know, this type of question is just general kind of knowledge, kind of factual memorization, little facts here and there.
So it's not made up of molecules?
Sodium chloride is not made up of molecules. Is not. And I might have told you this, I might not have, because my memory's not good. So I'm one of those people. Did I take my vitamins this morning, or did I not take my vitamins this morning? I forget. But I might have told you that I was watching the news and somebody said molecules of copper. Molecules of copper. You know, they want to take copper down to the individual molecules. Does that make sense to you? No. Because we know the definition of molecules is discrete unit. And so, well, how do you know? Well, you don't know because you have to memorize little facts, you know, here and there, and then we'll see some patterns. And so we got to start memorizing little things, and eventually we'll build up enough knowledge that we can figure out what forms molecules, what doesn't.
43. What did you get for the temperature?
30 times 10 to the
30 times 10 to the 3? 30,000 degrees C?
No, degrees K.
Or, oh, okay, we wouldn't put a degrees K over there, but just a K. 30,000 Kelvin?
Or 29,527 degrees C.
29,000.
So you can only have 2 sig figs, so 30,000.
30,000 degrees C. Okay, is that what other people got?
Yeah.
30,000 degrees C. Let me see. We need some points. Do you know what the temperature of the sun is? The sun is only 5,778 Kelvin surface temperature. And therefore, boy, we need the power of 6 suns. 6 suns. We need the power of 6 suns to melt that, or to get the pressure high enough. So that, but it's hard because numbers are hard. So this is why we've got to memorize certain little things, like the temperature here. The actual internal temperature of the sun is hotter. The internal temperature is approaching this, 30,000 kelvins.
I got 3,000. I got 3,000.
3,000 Kelvin sounds better. 3,000 Kelvin we should be able to get. 3,000 Kelvin and the minus 273 would give us 20,
Oh, I added an extra.
2,727 degrees C. 2,727 degrees C. Did anybody get something else? All right, let's do this one. I just want to double check this one because we're getting different results. More. All right, so T1 is 25 degrees C, which is how many Kelvin? 298 Kelvin. V1 is 50 liters. All right, P1 is 200 psi. Calculate the temperature at which the gas will be at 2,000 psi. So P2 is 2,000 psi. T2 is unknown. V2, what is V2? Yeah, I didn't give you V2, but we have to assume it's going to be the same. We're going to assume that the metal cylinder does not collapse or balloon out, that it's strong enough to withstand changes in pressure. And usually they are. Usually what happens is let's say, so we'll get T2 is equal to P2 over P1 times T1. Is that correct? And so P2 is 2,000 over T1 is 200 times P1 is 298.
But then you have the volume.
Oh, where's the V? Okay, the V is here. P1 V1 over T1 is equal to P2 V2 over T2. We'll put in the V here, 50 liters. V2 is 50 liters. And so the 50 liters cancels. In other words, V1 and V2 are the same. And so we can simplify this into P1 T1 is equal to P2 T2. And then solve for T2. T2 is equal to P2 over P1 times T1. So this comes out to 2,980 Kelvin.
Can you do that, but keep the 50s in? Because I think that maybe I got an extra 0.
keep the 50s in?
Yeah.
Yeah, we could do
Try
that.
solving it with this.
All right, so if we solve for T2, this is going to equal B2 over B1. So it's going to be 50 over 50 times 298 Kelvin. And that's going to give us 2707 degrees C. How many sig figs are we left? Yeah, maybe 2700 degrees C. That's good, because do you know what the flame temperature is roughly for the methane? Flame? Flame temperature like this is roughly about 800 to 1000 degrees C. Probably the melt. What does steel melt at? Do you know what steel melts at? It's probably mild steel, not stainless steel. Steel melts at 1427 degrees Celsius. So we might feel safe here, but we aren't really safe, because if the temperature gets to 1400, the cylinder is going to melt. But those are things you think about when you know some numbers. The only reason I consider melting is because I know the roughly the temperature of melting. Do you know what metal has the highest melting point? Yeah, platinum has very high. Platinum, iridium. Do you know what platinum's melting point is? I know it. It's 1600 degrees C. I know that melting point. Why do I know that? I know that because of electric furnaces. I used to work with electric ovens, and there's a certain temperature limit you can reach. With a platinum furnace, you can get almost 1600 degrees C. And so I used to use a platinum furnace. At the time, the platinum furnace was probably a $20,000 furnace, but now that's probably $1 million furnace with the amount of platinum inside there. And the way platinum prices skyrocketed, it's like gold, you know. And so anyway, platinum versus a regular electric oven, how hot can you get with a regular electric oven before it melts? You know, why do they use tungsten in light bulbs? Yeah, it has a very high melting point. I think the tungsten's melting point is actually I forgot tungsten. I used to know it. But tungsten is very high melting point, and it's cheap. Why not use platinum? Platinum has an even higher melting point, but it's just too expensive. But you know, if you have little bits of knowledge memorized here and there, then you can make connections. And if you can make connections, then you're going to be much better off. So
is chapter 5 homework due tomorrow? Are we going to do each class?
yeah, chapter 5. Actually, that's what I was going to do. Chapter 5 today. Chapter 5. Did you do 44?
No.
45?
Yes.
46?
Yes.
All right. The chapter 5 homework, we could take the chapter 5 homework is a pretty short assignment. And when you look at this, okay, did anybody finish chapter 5 homework?
No.
We're going to do it in class. This is what I was going to do.
Are we being tested on that?
We're going to be tested on chapter 5, but maybe what I'll do is I'll limit the number of sections we're going to be tested on in chapter 5. Probably what I'll do, let's take a look at chapter 5 that we're expecting you to see. I'm not going to do this for every test. It's just for the first test, you know, the first test, to have this much review. You know, basically you should be doing review at home every day for the test. And you shouldn't cram. This is called cramming at the end, you know, you're building it up. But we got to cram. This is why I was doing the daily review. But let's take a look at the chapter 5, and then we're going to do Dalton's, yes. Dalton's, yes. Rutherford, yes. Isotopes. Do you want isotopes on this test? Okay. It just means I'll put isotopes on the next test, which means, well, this is what I did last semester. I put isotopes on the next test, so you'll have that, but that means you'll have more information on the next test. If isotopes is easy, then you want it on this test. If isotopes is hard,
Well, like, what type of questions did you ask about isotopes?
Yeah.
how many protons, how many neutrons?
And would you give us the mass number, the atomic number?
Yeah, I mean, you'd be doing a table like this.
And would you give
You know what? Maybe we'll do isotopes on the next. That way, it's similar to last semester. Last semester's I cut it as well,
Okay.
and so we'll just have it.
Until before isotopes.
Yeah, up until and before isotopes. Because if you look at the sample test, there's Rutherford, there was, etc. So we'll just have it the
How
same.
about the homework?
The homework, you just turn it in with the next test. I collect the homework complete, so you can turn in the entire assignment with the next test. I don't want to with the next test. But does that mean you should ignore some of the homework problems? No, you should do the ones that are pertinent to the early sections. But you know, I screwed up the homework because I did the homework based on the 5th edition, which I had at home. I left my 6th edition in class, so I was looking at that.
Are you gonna do the homework?
So, no, I decided I'm not going to redo it, but if some of the questions are just, one of the questions doesn't make sense. You'll see it. But don't get too hung up on the questions. If it doesn't make sense, the questions were supposed to be simple because this is supposed to be a short, simple assignment. But if the question looks weird and it's not making sense, it's probably weird and not making sense because I read it and I thought, what are they asking for? And then I read the answer. You know, it's like, you know, what features of the CRT made the discovery of the electron possible? What features of the CRT made all the features? You know, I don't know. You need everything. You need a vacuum. You need a voltage source. You need this. You need that. And you know what they said was what made it feasible is the invention of a Crookes tube. Well, no, you could have used a soda bottle, a glass soda bottle for that, and so you'll see it. It's a weird. That's the one that was weird. So don't get too hung up on that. I wouldn't ask you that type of question anyway.
For the exam, are we meeting inside the lab?
We're meeting inside the lab. This room is actually occupied on Thursday, so we wouldn't have the full 3 hours. Yeah, the official department policy is we want to keep this the same as standardized tests. The standardized tests like the MCAT, LSAT, GRE. So you know we want to make sure that you're comfortable not using graphing calculator. But you know you invested a lot of money. Graphing calculators are $100, $200. You should be able to use them. But since when the standardized tests let you use them, then we'll let you use them. I guess that's the. For now, just use your backup calculator. Do you have a backup scientific calculator?
Every day.
Thanks.